So what kind of role do dust particles really play in atmospheric chemical reactions?
In traditional atmospheric chemistry theories, secondary organic aerosols, SOA for short, are believed to form mainly in tiny submicron particles, especially inside water-containing cloud droplets. But this groundbreaking study, led by Professor Weijun Li at Zhejiang University, boldly challenges that old view. After years of fieldwork and lab analysis, the team discovered something astonishing. During dust storms, more than half of the water-soluble organic carbon, WSO, which is mainly SOA, actually exists in supermicron particles.
Wow, so what exactly are secondary organic aerosols?
Secondary organic aerosols, or SOA, are tiny particles formed when volatile organic compounds in the air go through oxidation and condensation. They're called secondary because they don't come directly from emissions, but form later in the atmosphere. And here's the catch. They're a major part of smog, and they have huge impacts on air quality and climate change.
But dust particles are coarse, right? How can they possibly take part in this process?
The key is aging. As dust drifts across the atmosphere, its surface often gets coated with calcium nitrate, and that coating absorbs water even under typical humidity. Suddenly, each dust grain becomes a tiny microscopic reactor, the perfect place for aqueous SOA to form.
So the change in the dust's surface properties is absolutely critical.
Exactly. Observations in Alishan, Xi'an, Qingdao, and Crete, Greece, all showed the same pattern. During dust events, WSOC in supermicron particles skyrockets, and it strongly correlates with calcium ions and nitrate. That means these organics weren't just sticking onto dust, they were born there through chemical reactions.
Fascinating. But how did they prove it wasn't just simple adsorption?
They used advanced microscopes, SEM, TEM, and nanosims. And what did they see? Only the aged dust with calcium nitrate coatings showed organic signals. Since calcium nitrate starts absorbing water at humidities above just 80%, which is almost always in the atmosphere, it creates the perfect watery film for molecules like glyoxal to dissolve and react.
Just 8%, that's incredibly low.
Exactly. That's what makes calcium nitrate so special. By contrast, salts like calcium sulfate or calcium oxalate need humidity over 90%. Under normal conditions, they stay dry, and reactions don't happen.
So what happens inside this watery film?
Several processes. First, water-soluble organics like glyoxal dissolve and get oxidized, often by OH radicals produced when nitrates break down under light. That creates less volatile organic acids like oxalic acid. Second, those acids can react with calcium carbonate in dust, locking them in as salts. Third, oligomerization occurs, molecules linking together into bigger, more stable structures. Step by step, the dust becomes a factory for new organic matter.
Incredible. Did they also model this?
Yes, they ran the impact global transport model. When they added glyoxal uptake on dust, the model matched observations much better. Without it, the model underestimated the role of coarse particles.
And globally, how big is the contribution?
On average, aqueous SOA from dust makes up about 16% of total SOA over land. But along the dust belt, from the Sahara, across the Middle East, through Central Asia to East Asia, it can reach 67%. Dust accounts for 28% of global aqueous SOA, up to 74% in the dust belt.
That's astonishing. So what does it all mean?
It means dust isn't just a bystander, it's an active player. It changes how we think about SOA lifetimes, global distribution, and radiative forcing. And beyond climate, it could affect cloud formation, rainfall, and even marine ecosystems. Because when dust with organics and iron lands in the ocean, it can change biological activity.
So in other words, this discovery is a real game changer.
Absolutely. Most models today ignore aqueous reactions on dust. This study proves we must include them if we want accurate predictions for air quality and climate. It's a breakthrough that could reshape atmospheric science for years to come.
This video is brought to you by the BMET team. Feel free to visit our video channel via WeChat.
Bye-bye.